The all or nothing law basically means that the action potential either fires or doesn't, and there's no in between. If threshold is met, you get an action potential. If threshold is not met, you don't. And the rate law goes along with that. The strength of a stimulus is represented by the rate of firing of an action potential in the axon. The size of the action potential is always constant. So the size of the action potential is always constant. It's basically the all or nothing law. So if we have a weak stimulus, and this represents our stimulus, then the action potential pulses. And now when we're looking at the rate of firing, we're going to condense down the action potential into just these lines to represent pulses. So the action potential pulses are going to be kind of spread apart and uneven. And that's because after firing a single action potential, we have to wait until enough positive charges pile up to once again reach threshold at the axon hillock to fire another action potential. However, if we have a stronger stimulus, that would be a much bigger depolarization, then we basically get to skip over the relative refractory period because we have enough positive charges ready so that when the voltage gated sodium channel resets, it can basically immediately open back up again and fire a new action potential, which is why we see them close together in space and in time like this, I should say. And I've modified this figure to show what we mean by a bigger stimulus, that this is actually a greater amount of depolarization. The refractory period is the period of time after firing one action potential where it's either not possible or not likely to fire another action potential. And this table is something you should be able to fill out on your own. And then if you have questions about it or if you want to check your answers, please do post it to the discussion board so that I can look at that with you or for you. This is from Neuroscience Online, and it's providing more information about the absolute and relative refractory periods. And what it's trying to show is that if you have depolarizing input far enough apart, you can get sodium conductance for each of them because the voltage gated sodium channel has had enough time to reset in between. But if you have two depolarizing stimuli too close together in time, you'll get sodium conductance once, but not a second time because that voltage gated sodium channel hasn't had an opportunity to reset. I really like this figure that shows the progress of the action potential through the voltage gated sodium and voltage gated potassium channels. And I really want to draw your attention to the fact that the voltage gated sodium channel has two literal gates. The activation gate, which is also called the M gate, and the inactivation gate, which is also called the H gate. The inactivation gate is what closes at peak, and that's what allows the action potential to basically stop going up, right? Because the activation gate opens and closes at threshold. So if we didn't have this inactivation gate, the channel would never close because sodium would always be coming in and trying to bring membrane potential to plus 60. It wouldn't ever have an opportunity to drop back down to close this gate. That's also why the voltage gated potassium channel doesn't need two gates, right? It opens and its impact is in the opposite direction of the voltage gated sodium channel, right? Potassium is going to leave the cell, driving membrane potential back towards rest. So it's going to repolarize and then ultimately hyperpolarize the neuron. This gate is slow to open and slow to close, but it's triggered by threshold as well. So the potassium leaving the cell is actually working in the same direction that will end up closing its own channel. It's important to think about the relationship between the disequilibrium that we have at rest and the driving forces that allow the action potential to occur. So the resting membrane potential at minus 70 millivolts is kind of one piece of the puzzle, But then the disequilibrium of ion concentration is the second piece of the puzzle to have both driving forces set up so that we ultimately can fire action potentials, right? And then the sodium that is entering the cell and the potassium that is leaving the cell through those voltage-gated channels ultimately need to get put back where they belong. We need to reestablish resting concentration of ions, and that's where we have to do some work. The sodium-potassium pump uses ATP to do that work, to push out the sodium that came in and to bring back in the potassium that left during the action potential. This pump is the most expensive thing that the neuron uses. It uses most of its ATP in order to reestablish and maintain the resting disequilibrium ion concentration. Myelin is found on many, but not all, neurons, and it allows for a process called saltatory conduction, which ultimately saves the cell some of that ATP energy by allowing the sodium-potassium pump to not have to work as hard. Myelin essentially forms fatty tissue that surrounds the axon in segments. Myelin is produced by oligodendrocytes and Schwann cells. You should be able to know which of these happens in the central and which happens in the peripheral nervous system. Once the myelin has been produced, its function is identical whether it came from an oligodendrocyte or a Schwann cell. It is relevant to know that one oligodendrocyte can myelinate lots of nearby neurons. So as I said, there are two purposes of myelin. One is to save energy in the form of ATP. The other is to save time. What we mean by saving time is that myelin, through saltatory conduction, increases the conduction velocity of the action potential. The action potential in a myelinated neuron travels faster than an unmyelinated neuron. So then the next question is, how exactly does myelin allow that to happen? How does myelin allow the action potential to travel more quickly? How does myelin decrease the use of ATP for the sodium-potassium pump? There's a really great Khan Academy video on saltatory conduction and another one on axon diameter and myelination. And you should absolutely watch both of those videos because they'll probably explain it a lot better than I do. But basically what myelin does is it decreases the capacitance of the axon membrane. So normally we have positive charges lining up on the outside and negative charges lining up on the inside. And when the action potential happens, we suddenly have a ton of positive charges entering. In an unmyelinated axon, we need to constantly regenerate those positive charges in order to move down the length of the axon. But in a myelinated axon, we have more of those positive charges that travel down the length of the axon so that we don't need to constantly regenerate. We only need to regenerate every so often at these empty spaces in the axon called the nodes of Ranvier or Ranvier. And this process again is called saltatory conduction because it looks like the action potential is jumping from node to node. We have passive movement of ions through the myelinated segment, and then we regenerate, and then we retain just enough positive charges so that we are still at above threshold when we reach the next node. This is a figure from a different source that I like because it shows the axon in sort of segments. Starting at the axon hillock, this is where we first have voltage-gated sodium channels. Sodium enters through those voltage-gated channels, and then through this local current, it depolarizes the next segment and opens the voltage-gated sodium channels there, and so on and so forth, right? Through all of these individual segments. Myelin allows that local current to have a longer distance, right? Sodium enters and enough of it can travel down here to reach threshold so that we can regenerate the action potential at this gap, right? So instead of having 3 segments of axon, we're basically having 1, 2, 3, where we only have to regenerate 3 times instead of 3 times in just that first amount of space.